We're back. Welcome to AP Calculus again. So, our guide looks like that. We've already talked about it. So, let's talk about our objective today. Quiet raised hand. What is our objective? Two people just yawned. Our objective today, Claire, yes.
Relate position, velocity, and acceleration and take the derivative.
There it is. So, quick hands again. Who's in physics? Everyone but Arrow, right?
Yep.
All right, so this will come very, very naturally to those people in physics, and I will derive some of the formulas that you use in physics from thin air. Maybe not today. So the A-B test has these types of motion. You have horizontal motion. Horizontal motion. So horizontal is at the X or the Y coordinate. Shout it out. It's the X coordinate, yeah, make sure you know that. And then we have the vertical motion. Which is the Y. I kind of gave that one away. So if I say a particle is moving on the Y-axis and it's moving in a positive direction, what does that probably mean, up or down? Up, okay, so that's kind of the most confusing part about that. Now we know. Okay, complex BC. We are all taking the BC test, so it is very relevant that I tell you this. We won't learn this until pre-calc, Claire, on your own once we start talking about that topic. Same thing with Arrow. But eventually, you're going to be doing these both together. Both together. Which sounds hard, and it's not that hard. Like, it's just an additional topic. It's a little bit mind-bending when you first see it, but this is doing things. I'll just give you an example. Like, you could do parametric motion. That's one of the two main things. And remember way back in the day when we were like, oh yeah, if you have a line that looks like this, that's not a function because it doesn't pass the vertical line test. All of a sudden, you can do a graph that goes like this, and you can take the derivative anywhere you want because you have calculus to take the derivative and you can go wherever you want. So it's kind of cool. Yeah, that's parametric motion. So you have values of x, y, and t. T kind of dictates what's happening with the values of x and y. But we'll do more on that at a later date. So how do you describe motion? So position, velocity, acceleration. Do those sound familiar? Giving me the giant thumbs up and smiling. Yeah, so the position, that's going to be your x or your y, right? You're talking about your horizontal or vertical, so you're doing your x or the y. And generally speaking, that is your position, your distance from your start. So I'm going to write here distance from start. And usually you start at like the origin or something easy. Very rarely do they say, start at x equals 10, y equals -3. You're usually going to be starting from the origin. I feel kind of silly defining position because you guys know it so well. Velocity, we know that is kind of the rate of the position change. And that sounds a little bit funny now that we're in AP Calculus and not in physics. You always think, oh, well, velocity is speed and direction, and then it's governed by these equations. No, that's just the derivative of position. Take the derivative of position, you get velocity. The rate of change means the derivative, which means velocity is the derivative of position. And vice versa, since we know how to go backwards and take antiderivatives, position is the antiderivative or the integral of velocity. I can go back and forth between these. Today we're only going forward. We're only taking the derivative. So that means acceleration. Anyone want to take a shot at it? It has the word rate in it. Rate of velocity change. Yeah, exactly. Yeah, so the main thing to take away from this part of the notes is to get from position to velocity, derivative. To get from velocity to acceleration, just take the derivative. And we've talked about second derivatives in here, which means the acceleration is the second derivative of position. All right, so lots and lots of times, I would say like 50% of the time on multiple choice, you will be given a graph. The other 50%, you'll be given a word problem. Let's talk about graphs. Let's make up a graph here. Let's do points at 1, 4 on that intersection. Let's just do all the intersections. 2, 8, 3, 12, and then yeah, 4, 16. I guess we can't go any higher. Let's just make it a flat line. We can make it a piecewise graph. Do your best to sketch a line through that. I have technology, so I can make it kind of a straightish line. I want this to be a straight line there, a straight line there that continues on and on forever. Well, maybe not forever. It's a real world problem, so you have to stop sometime. Oh, thank you. Making it a precise graph. I'm just randomly saying, here, I've made this position. And you can kind of make a story that goes with this graph if you want. My story is, Mr. Sandell is skiing up Tamarack Mountain at a constant rate, and then he takes a break after 4 seconds to catch his breath. I'm not moving anymore, right? Because I've stopped moving. My position is no longer moving because I'm taking a break. Yes. Okay, so let's look at that same graph in terms of the velocity. Again, this was a position graph. Then we're going to do a velocity graph. Then we're going to do an acceleration graph. Note the units on the left-hand side. The units were feet, then feet per second, then feet per second, or feet per second squared. You're just really dividing by seconds again because you're taking the derivative again. Oh yeah, before we move on to velocity, let's go ahead and define what these functions are. So this is a function. Let's pretend obviously I'm moving at a diagonal because I'm going up a hill. Let's pretend I'm only looking at my x coordinate. Like how fast am I moving from like a satellite view? So I'm going to say x of t. I have to have some variable. I can't have x of x. That would be confusing. X of t is equal to the piecewise function because there are 2 pieces here. So I should have 2 functions. What's this first function on the left-hand side? What t? Give me the slope of it, the y-intercept. What is the slope of this line right here? Shout it out.
4.
Yeah, so it's going to be 4t. What's the y-intercept?
1.
0. Yeah, 0 down here. So just 4t plus 0, just 4t. So there's the first equation, and that's it's between this t coordinate of 0 and this t coordinate of 4, so between 0 and 4. So 0 is less than or equal to t is less than or equal to 4.
How come we're using x instead of y for that?
Oh, I could have been talking about my elevation change as well. You're talking about this x right here, right?
Yeah.
I just randomly said, let's talk about my x instead of my y. It is totally arbitrary. And then what is this other function? This is a constant function, a little bit easier. What is the height of the line, guys?
16.
There's the answer, 16. Okay, the constant function of 16, and where does that start? It starts at 4. This line right here starts at 4. So 4, and I'm going to do less than because I've already used my equal to sign down here. And then I'm just going to say t, and I don't know, just something random. I'm going to go out to 20, sure. I just totally randomly picked that 20, by the way. Cool, so now we have a piecewise function in terms of the algebra, the notation, and we have a graph. So let's see what happens when we take the derivative of this position graph. And you guys that are in physics should have seen these before. When I look at the velocity graph, what's happening? Well, let's take the derivative. The derivative of x, the derivative of position, you guys will all shout out, is velocity. Derivative of position is velocity. So instead of an x sub t, I'm going to do v sub t. Use this space up here, you're not going to be writing up there. So v sub t is now the derivative of, it's like x prime of t, right? It's just a different letter because it's velocity instead of position. It's still going to be a piecewise function, and when we take derivative of piecewise functions, take the derivative of the left piece, derivative of the right piece. So derivative of 4t with respect to t is 4. Derivative of 16 with respect to t is 0. And it's still for the same 4s. I can copy paste. I love technology. For the same intervals. And then graph it. Okay, well, these are both constant functions, Mr. Sandell. They're both just flat horizontal lines. One is a horizontal line that has a height of 4. So I come over here and I have a height of 4, and that starts at 0 and ends at 4. Starts at 0, ends at 4. And then the next one is a height of 0, and it goes on forever and ever that way. The key thing that's happening in this graph is open and closed circles, and if you forgot those, I'm going to leave them up on the top right of the cubby thing up here. Do you guys see my open and closed circles? You know if you're equal to or not equal to. A closed circle, should that go on the constant function of 4 or the constant function of 0? 4, yeah, because we have an equal to sign at 4. So this is going to be an equal to a closed dot, and down here, an open dot. Which is
Where do we have an equal to?
equal to 4 is right there, yeah. And then not equal to 4 right there.
Or how did you do zero?
Down here, we do an open dot at 0, yeah.
Over the other,
Where
where x is
x is equal to 0. Well, you actually are continuous at this point because you are equal to 4, so this height is still true. There's no open dot.
but you can't find the slope there.
It's, yeah, you can't find the derivative there, and that's kind of evident in this graph too. It's harder to see here. All you can see is a sharp corner. Down here, it's much more easy. It's like, oh, well, that's definitely not even continuous, therefore it can't even be differentiable. You have a giant hole in your graph, a gap.
Wait, how do we know that the equal sign goes on the first function and opposite?
So the first function is 4t, and that has an equal to 4. The second function has a 4 with no equal to sign.
But why is it on the first function?
When we were graphing the first function is 4t, right? This function right here.
Yeah.
I just, like, I think you're asking, like, how did I come up with this?
How did you decide to put the equals?
I just randomly put it there.
Okay.
Just for the sake of an example. Sorry about that.
Okay.
So now we have an equation for velocity. Let's go ahead and find an equation for acceleration. Acceleration with respect to t is equal to, we don't even need a piecewise function here. Why?
Because it's all zero.
It's all 0. 0 for 0 is less than or equal to t, which is less than or equal to 20. Which means now it's continuous again, which is kind of cool. We went from something that was not differentiable but continuous, something that's neither continuous nor differentiable, to something that is both continuous and differentiable, which is not quite true, but I mean, in the graph it looks like it, right? Algebraically, it doesn't work out. Should still have an open dot, I suppose, at 4 if I'm being technical about it. But it looks continuous. There it is. So now you know how to convert between graphs. Good review if you were in physics. Look at the equations, see what happens. Let's test some people. I'm going to go through everyone. Let's start with Arrow again. We'll go counterclockwise. Arrow, is my velocity increasing or decreasing here at 1? If I didn't even have a velocity graph, is my velocity increasing, decreasing, or neither right here at 1? Neither. It's neither increasing nor decreasing because my acceleration is at 0. Let's go to Claire. Is my position changing to be more positive or more negative at 1? More positive. Stego, is my position becoming more positive or more negative at 5? Talking about position. It's my rate of position. Trick question. It's at 0. So neither. All right. And then Geo, is my, I guess I'm going to have to recycle. Is my position increasing or decreasing at time equals 1? Increasing, okay. And it's just based on your height at this case. Let's move to an actual example down here. So we have a car and it has a graph of acceleration for that car. And of course it's piecewise defined because it's broken up into lots of these segments. I want to know the velocity of the car.
Yes, the care.
Is the velocity of the car increasing at t equals 15? This is an actual AP question, which is interesting, right?
It's like Care Bear driving the car.
Oh, that's what it is. So here's 15. So I'm really right here on my graph. So at this position, this is an acceleration graph. I'm asking about velocity. Is my velocity of the car increasing or decreasing at time equals 15 seconds? Who wants to take a stab at it? Increasing, because it's sloped up, right?
But it's
Not
negative.
quite.
It's in the negative section.
Yeah, so whenever you're looking at these and you're going backwards one step, it's all about the height. Is the height above or below the x-axis? Because the height is below the x-axis, or the t-axis, I suppose, it's actually decreasing. So the answer here is decreasing. And then they ask why, explain, and the answer is because a of 15, and I write it as a of 15, but I really say height at 15 is negative, is less than 0. All you care about is the height. And it's going to be very repetitive on the homework. You really care about the heights here. Let's see one without a graph. Example number 2. Say I just have some function of x is 3t to the power of 4 plus 16t minus 19. That's a particle moving along the x-axis, horizontal motion. I want to know what is the acceleration when t equals 2. Wait a sec. I'm asking for acceleration, but I'm giving position. How do I get to acceleration from position? You have to find the derivative to get to velocity, derivative again to get to acceleration. So let's write it out. Velocity of t, I take the derivative. Gio, you got this for us. Take the derivative. 4 comes down the front. 12t to the power of 3 plus 16, and done, right? Yep. All right, and then let's go with stego, find acceleration. The equation of acceleration. Yeah, I should have curved my t's a little bit. T squared. And Claire, you already participated. Arrow. Therefore, what do I do next? When t equals 2 means what?
Plug in the t for the, yes.
There it is. So I plug in 2. So a of 2 is equal to 36 quantity 2 squared. Yeah, Claire, can you just do this for us? 144. Thank you. And Claire, what would our units be on that? We don't have any units. Let's say units per what?
Second squared.
Per time squared, yeah. Perfect, because it's a unit of acceleration. All right, so this is the point where you get to whip out those calculators.
You get to take these home for homework?
Yes, and I need to make sure that people have the right number of calculators. So alphabetical. Arrow is first, but you have your own calculator. Next is Claire, Gio, and then Sego. So Claire, you need to make sure to have number 1. So take whoever has number 1.
I have 2.
And then Gio should have 2, and then Sego has 3. You are responsible for those calculators. They cost $115 plus tax. Yeah. I spent roughly 150. No. I think 150 after shipping and tax. But they cost a lot of money. If you break it, you buy it. I spent roughly a third of my money for the entire year on those calculators.
Because we're your favorites.
I mean, it's not a lie. Okay, so whenever you see this, I'm going to try to do better this year. Arrow knows this from frustration last year. Do I get to use a calculator or not? If I put this calculator symbol, that means you get to use your calculator. So on the back of your homework, you'll notice these calculator symbols start popping up. You'll need to use your calculator. All right. If you don't have a calculator, assume that you don't. And if it's still too hard, then ask me. I think you might have missed one, Mr. Sindel. So we're going to practice this one. And Arrow, follow along to the best of your ability. I'll open up my other calculator in a second. What is going on with my... There it is. Okay, so open up your calculators. We need to, well, maybe first analyze the question here.
So how do you tell if it's the brightness or it's just out of battery?
It's usually the battery because very few people are going to troll you.
Okay, it's out of battery.
I will get you a different one. You have this entire drawer full of old TI 83 pluses to choose from. Choose wisely. On your calculator. No, sorry. We're analyzing the problem. We have this function and it's a particle's position because it's x of t. Horizontal motion. And we're trying to find acceleration. So how do we get from position to acceleration? Derivative twice, right? And I feel like that, I know you can do it. It's been a while. Okay. So first we need to type in our equation. So hit your y equals button, top left.
Whoa.
Is it gonna?
Colors. Oh, I love this color.
All right. So you're going to type in this equation. The variable x, t, whatever your variable is, it's the same button. It's this x, capital T, theta, n button.
Should it? We don't have the. At least I don't have the x. I just have y1, y2, y3.
Oh, am I? Hold on. My mode. I'm in parametric mode. Thank you for catching that. I didn't even see that. Function. Enter. Now your y equals looks like that. Okay, so thank you, Claire. You're going to type in your equation, which is you're going to have to use x in this case. That's fine. X times, and whenever you do times, you don't actually have to enter anything. X times, and it's going to be natural log. Natural log is down here, bottom left. Natural log of that same x button squared, and then the squared button plus 1. You don't need to end your parentheses. It'll know what's going on, but there it is. There's your equation. I'm pretty sure you don't have to hit multiply. I'm trying to do as many shortcuts as possible. We'll learn from it later if not. We have now typed in our calculator the equation. Now we need to take the derivative. We all have this same equation written. All right, so now you can get out of that. To get out of this window, second mode or second quit. You can see the blue quit up above. So second mode, that gets you out of there. We now need to say, hey, take the derivative of the derivative and then plug in 1.5. So we do that. We say math.
Oh, math.
And then I think it's math. For us, it's you can just type in 8 or you can scroll up to hit 8. Math 8 is the faster way of doing that. Take the derivative, so math 8. And I realized that I don't know if this question would be asked. So we say, okay, what are you taking the derivative with respect to? You're taking the derivative with respect to, oh, sorry. Math 8.
Math 8.
Math 8.
Thank you.
So we all have this screen right now, right? We're taking, no?
So I pressed the second and didn't do anything.
Let's see what you got.
Yeah.
So, second.
Oh, okay.
Math. So we're going to say now we're taking the derivative with respect to x. We have to type in x. And then what is the function that we're taking the derivative of? Well, we're taking the derivative of this y1 function. You don't have to hit this, but come back here. This is the y1 function, right, that we're trying to take the derivative of. So in this window right here, we now need to say we're taking the derivative with respect to x of y1. To get there, it's vars. It's your, I think it stands for variables. Variables, we want to go to our y variable, so we have to hit the right arrow key. And then, oh look, a function. So we hit enter, or 1. And hey, y1. We're taking the derivative of y1. At x equals what? Well, there's a problem with the writing, and I made this question up. So I should have changed it to what is the velocity of the particle. I'll come back and change that in a second. But we're going to type in 1.5 here. At x equals 1.5. And hit enter. And it'll tell us, hey, when we take the derivative and we plug in 1.5, we get 2.563. And as a kind of all-encompassing rule, whenever you're doing the AP Calculus test, round or concatenate, round or truncate, there's the right word, to 3 decimal places.
What's the second one?
Just don't even round, just do 3 decimals. Cut off and go, yeah. I always round because it's a good practice to know. 2.563. 3 decimal places, 2.563. So I come back here and I say, can we change this problem to make it a little bit easier?
Yeah.
Let's change this to velocity.
Okay.
So we took the derivative to get from position to velocity, and we can say that the derivative d dx of x of t is equal to v of t. And then therefore v of, I'm just showing my work here. You don't have to do all this work. You can just write your answer out as long as you got it. V of 1.5, and we got that right here, 2.563. 2.563. And then there are no units that we have to worry about, but it would be units per time. That's the only operation that I think you need for the homework tonight. How to take the derivative and plug it in a point. And for arrow, it's a little bit harder. Did you figure it out?
Eventually.
Cool. Yeah, for arrow, she doesn't have this nice setup. She just has this function. You have to put in these values at random spots, x, y1, and 1.5. And if you get it wrong, it'll give you the wrong answer. So you guys can start on the homework. I'm going to pull up the other calculator to see if it still works and then teach the YouTube audience how to do it on the TI-83 pluses. So let's see, WABBIT EMU. And I can show you guys what arrow sees too. It's kind of cool. So that is correct, yeah. So arrow enters this. Let's go ahead and, oh, I can minimize you. I'll make you go away. So this is going to be x times natural log of x squared plus 1. So I have my function. You don't need that last parenthesis. Second mode to get out of it. I'm going to do math 8 to take the derivative. And then you take the derivative with respect to x of your vars, right? Enter your y1 variable at what point? And it was 1.5, right? 1.5, 1.5, and you should get the same answer as, nope, I got it wrong.
I think the y and the x are switched.
Okay, so I should
I didn't look at what you actually did, but I'm pretty sure the
y1, so I can insert, second delete will insert, and I do x, comma. All right, so let's try that. There it is. Okay, yeah, so you have to do the derivative of y1 with respect to x of 1.5. There's how you enter it. So if you guys want to take a quick peek of how harder arrows is, this is what she sees, and this is what you guys have. The difference between them is the reason that John Wynn highly recommended getting updated calculators. You just have to enter them all in the right order. And each function that I'm going to be teaching you, Arrow has to memorize the right order for each of those functions.
This reason about how do you get out of y value thing?
Second mode. Yeah, so if you're right here, second mode will get you back to this main screen.